Okay, in this video we will be doing the first parallel circuits practice. So let's get started on that. Parallel circuit is shown below, and it wants us to find a bunch of stuff about that circuit. Great. So let's start with some colors. I'm going to say this is my zero potential on one side of the battery. And this will be my, is that 100 volts? 100 volts. 0 volts on this side. So 2 loops. An electron could gain 100, lose 100 here, or it could go around, gain 100, and lose 100 over here. One thing I noticed looking at this, these are both the same resistance. So I should expect same current through each path here. Determine the potential difference across each resistor. Determine the current. Okay. So I'm going to make a table just to keep things organized here. Resistance, current, delta V, and power. And I can do that for the first, the second, and for the battery. The reason I wrote these in this order, RI, VP, is because I know Ohm's law, delta V equals IR. So delta V, I, and R. So this times this equals this. And I've got P equals I delta V. So I times delta V equals P. So that times that equals that. So this is a little fun way to organize everything and also make some of the algebra easier. All right, so what do I know? I know this is 40 ohms. I know this is 40 ohms. Battery doesn't have a resistance, so I don't have to worry about that. The delta V, the battery is adding 100. Each resistor is taking away 100. You could put negatives in front of these if you wanted to. All right. Note that these don't need to all add up in a parallel circuit because an electron is not going to go across both of these resistors. It's just going to go across one of them as it travels through this circuit. Okay. I. Well, look, I've got a resistance and change in voltage for each of these, so I can figure out how much current is necessary to make that happen. So for a 40 ohm resistor to change from 100 volts to 0 volts, that would be 100 divided by 40, 10 over 4, which is 5 over 2, so 2.5 amps. And that would be the same for both of these because they both have the same delta V and the same resistance. All right, let's go back and add what I just found. So that's whenever I find something, it's nice to go and draw it on my circuit. So this one has 2.5 amps going through it. And this one has 2.5 amps. When I draw this, really, I mean, this whole spot is 2.5 amps because it's one loop, 2.5, 2.5. So does that let me add anything else here? Well, if this is 2.5 and this is 2.5 together, as they come together here, I'm going to get 5 amps going through this top part of the circuit, right? Because it's going to be 5 going to the battery. Then it's going to split into 2.5 one way and 2.5 the other way. So I can say my current, my total current from the battery, 5 amps. Okay. Power. Well, now I'm just doing a bunch of P equals I delta V here. Because I found all of this stuff, I can just use the first equation. I don't have to use this. We might also say we could use this. We could use that one as well. 100 times 2.5 is 250 watts joules per second. 250 watts joules per second. 500 watts. These would be negative technically. And here, these do need to add up. Power from the battery does need to equal the power from each resistor. Otherwise, I'm somehow breaking conservation of energy. So, boom. I can see I did the right things because in the end, when all is said and done, the power added by the battery equals the power dissipated by the resistors. Okay, we have a very similar situation here. We're asked to do the same things, except here the resistors are not the same. So let's do a quick 0 volts. It's going to be 50 volts because I have a 50 volt battery. No resistance here, so that's all the same potential. Same deal here, nothing taking away the potential along those wires because they're perfect wires, just like the students watching this video. Let's do a table again. I think it's a good practice to get into: resistance, current, voltage, power. RIVP. Too bad it's not an RIP table. That'd be funny. So I need one more for the battery. 1, 2, and then my battery. My battery is 50 volts. That's all I know about my battery. It doesn't have a resistance. I have a 15 ohm. I have a 30 ohm resistor, and they're each changing the voltage by 50. Because they're both taking it. Electron gains 50, loses 50. Gains 50, loses 50 around either of these loops. Current. Well, changes it by 50, resistance of 15. Ooh, I did not make the numbers nice. 50 divided by 15, 3.33. 3.3 amps. 50 divided by 30 is going to be half of that. 1.6. We'll do another decimal here. 1.67, round it up. Amps. All right, so let's add that through this 15. I'm getting 3.33 amps. Through this 30, I'm getting 1.67 amps. Great. Conservation of charge says if I have 3.3 coulombs per second coming in here and 1.67 coming in here, together, going out, has to be these two added up. So 3 plus 1 is 4, and then this is another 5 amps. So I guess the math did work out okay. 5 amps of current, and I can see that going around. 5 amps, splits 3.3, 1.67. 5 amps. And then again, in this example, power is just doing some multiplication afterwards. So we've got 3.33 times 50. $166 watts. 1.67 times 50. 83.5, 5 times 50 is 250 watts. Resistors take away, batteries add. And if I were to add these, 166 plus 83.5, I get 249.5. So because I rounded as I was going along, I get basically the same thing, negative 250, positive 250. So it means I probably did the math right. Parallel circuit is shown below. Determine the current through each resistor, determine the resistance of each resistor, and determine the power. Well, my method is going to be the same regardless. I'm going to look at what my potentials are. I'm going to say before the battery is 0 volts, so after the battery 6 volts of potential, and it's the same along any spot with no resistance, nothing taking away energy. All right. Let's make a table. You don't need to make a table. You could be doing each resistor. Like right here, I could say, okay, resistor 3, I see it's changing it blue to red, 6 volts, current 3 amps. Resistor 3, I could say delta V equals IR. So 6 volts equals 3 amps R. R equals 2 ohms. And I could, write all these next to each resistor, all this information, but you'll see, especially, when we're in here, we don't really have a lot of room to write down everything we know about each resistor. Like so this one, I could say delta V for this resistor is 6 volts. This one's also 6 volts. And in here, I could find the current. I could say delta V equals IR. 6 volts, 3 ohms. I'm going to get I equals 2 amps. But you can see it's very messy to try to do it inside the circuit like that. You don't really have a lot of room to do that. So that's why making the table can be helpful. Delta V equals I times R. Power is I times V. Oops, this was R1. Was this one labeled already? Uh-oh. I erased the back up until we see what was there originally. Okay, yeah. I did know the resistance. Ri delta V P. 3 resistors and a battery. Resistor 1, 2, 3, battery. Resistor 1, 3 ohms. Resistor 2, don't know it. 3, we found it, but we'll find it again. Battery doesn't have resistance. 6-volt battery. These are all taking away 6. And be careful, when we get to more complex circuits, it won't always follow this pattern where these are all the same as the battery. All right, so we were able to find for R3, the current is 2 amps. And we did that by saying delta V equals IR. So 6 volts divided by 3 ohms gets me 2 amps. Oh, whoops. Oh, back up. It wasn't 3 ohms. Oh, no, actually, no. Gosh. Yeah, 2 amps. But this is not R3, this is R1 I'm doing here. Sorry, so this is 2 amps going through here. So we can add that and say 2 amps. R3 we found was a resistance of 2 ohms because we knew the current. We knew the current here was 3 amps. So I look at Ohm's law, I say 6 volts, 3 amps. This has to be 2 ohms. All right, and they also tell us the battery, there's 11 amps going through. here. Great. So how does that help me? Well, 2 amps going through here, 3 amps here. So this needed a split. It split here, 2 amps here. That means 9 going this way. And the 9 gets here, I have another junction. Splits again. 3 amps one way. It's got to be 6 amps the other way. Man, my A's are 6 amps, 9 amps. Okay, so going through R2, 6 amps. So it must have a resistance of 1 ohm, 6 volts, 6 amps, 1 ohm. 12 watts. Here I'm doing power equals I delta V. 36 watts. 18 watts. 66 watts. And we can check 12 plus 36, 48. 48 plus 18, 58, 66. Power in equals power dissipated. Each bulb in a string of lights has a resistance of 100 ohms. Connected in parallel, attached to a 1.5 volt battery. Battery can do 0.3 amps. So we're going in parallel here. So I'm adding light bulbs like so, and so on, however many I need. So in parallel, based on what we saw previously, we can see that each of these light bulbs is going to have a delta V of 1.5 because the battery is adding 1.5 volts. Each light bulb needs to be taking away 1.5 volts if the electron goes through that loop. So what is the maximum number of bulbs that can be added without destroying the battery? So we saw from our investigation that each light bulb I add gets a certain amount of current, and the current from the battery is the sum of all those currents. So this one plus this one, and so on, in order for it to be able to power all the light bulbs. So let's find the current through any light bulb. So each light bulb has a delta V of 1.5 volts. Has a resistance of 100 ohms. So the current through each light bulb, for it to operate correctly, 1.5 volts equals I times 100 ohms. 1.5 over 100 is 0.015 amps. So that's the I through one of these bulbs. So let's label that. So it's different from the I through the battery. All right, so each one needs a current of 0.015 amps. So the maximum the battery can do is 0.3. So how many can I get and have a total current of 0.3? 0.3 amps equals, each one is 0.15, whoops, amps, and then times the number of bulbs. So we'll just call it X. X equals 0.3 divided by 0.015. 20 bulbs. You can hook up 20 bulbs before it's too much current for this battery to handle. All right, cool. See ya.